Today we will consider descriptive statistics, the first part. At the end of the session, these are some of the objectives that I thought would be important for the audience. By the end of the session, should be able to define what descriptive statistics is. What is the difference between descriptive analysis and inferential analysis? What are the differences? Should be able to identify and explain key descriptive statistics. More importantly, is to be able to outline the steps involved in conducting the descriptive analysis in a systematic manner. And though the last objective is to be covered in a separate session, I'll just give you a brief overview of how then do you visualize the outputs of the descriptive statistics. We're going to have a practical example of how to perform the various descriptive statistics, but first we'll try and set stage by considering certain important basic concepts. So when you're looking at analysis or statistical analysis, you usually have two main arms. This is descriptive and inferential statistical analysis. Let's consider the image on the right. The role of research usually is to be able to give information about a population, about various aspects of a population. Often the population may be too large to be studied. Therefore, you end up studying a representative sample of that population. And this is what we refer to as a sample here. So you may not be able to study all Kenyans, but you can be able to perhaps get a representative number that we refer to as a sample. And I think this was covered. How then do you ensure that the small proportion of people that you've picked, that process of picking was done in a manner that ensures that this sample is representative of the population, because at the end of the day, then whatever information you get from the sample, then you'll try and see how then does it relate to the entire population. So that's the role of sampling. Now, the role of this descriptive statistic usually is to describe, essentially to summarize data regarding the sample, the small proportion of the entire population that you are studying. You are going to be able to summarize and organize information about this small category of study subjects through descriptive statistics, right? For example, you'll be able to say that of this sample that you studied, for example, half of them were male, majority of them were elderly. That's what we mean by descriptive statistics. So you're essentially describing the sample. To be able then to relate the findings of the sample and try to generalize them to the population from which the sample was drawn, then that is what we refer to as inferential statistics. We'll be trying to say the features we've seen in the sample, how well do they relate to the general population? If we are to compare this, if you are to look at this thing that you're seeing in the sample, would it be the same as in the general population, right? For example, if you are to compare males versus females with regards to smoking status, for example, in the sample, how then would it be in the general population, right? This is what we refer to as the inferential statistics. So for today, we largely focus on descriptive statistics, whose role is to summarize and organize data of a sample to try and understand its main features. So two main purposes. One is to provide you with a snapshot of data. Essentially, it gives you an overview as to what are the general characteristics of this sample that you that you got. It helps to identify these three things, and these are very important. One is patterns, right? Assuming you are looking at a study trying to identify the prevalence of diarrheal diseases, for example, in informal settlements in Nairobi, for example, and you decide to study two informal settlements and about 1,000 children there, and you come up with a study where of those 1,000, maybe over a period of time that you studied, then 50 had or developed diarrheal diseases, for example. Of those 50, then you can be able to identify patterns. So perhaps you could say that maybe the ones who developed the diarrheal diseases were more likely to come from households that did not have a good water supply, for example. So in your data that you'll have collected, then it means that perhaps you collected data on a water source, for example. And if you look at the 50 who got diarrheal diseases, you'll realize that maybe 40 of these 50 came from households that did not have good and reliable, clean source of water, for example. Then you'll be able to identify a pattern. You start asking yourself, could it be this water source that is responsible for the diarrheal diseases? So that's one of the importance of descriptive statistics. By doing descriptive statistics before inferential statistics, then you can be able to identify errors. For example, if you are to generate mean age of this sample and you find that perhaps the mean age is has a very wide standard deviation, which we will mention at some point in this discussion, then you ask yourself, is it that the value I'm getting is inaccurate or not precise because I've entered an erroneous value, for example, or are there data that is missing, for example? Then by just doing simple descriptive statistics, then you may be able to identify such errors before you proceed to do the more complex analysis that is inferential statistics. And then, of course, distribution. This is a very important concept because how you present data, how you eventually do the inferential statistic is determined primarily by one of many things, including the distribution of the data, right? From descriptive statistics, then you can be able to say, is this data normally distributed or is it non-normally distributed? And we shall see what we mean by normal and non-normal distribution and what is the implication of those various types of distribution when you're reporting descriptive statistics and when you're performing inferential analysis. So this, in a nutshell, is what descriptive statistic is all about. Of course, at the end of the day, we all are consumers of data. Some of you may have come across the famous KDHS, the Kenya Demographic and Health Survey statistics, usually released, I think, every 4 years. Most of the data there are usually presented in a descriptive manner. So you'll have data about the general Kenyan population, right? Frequencies, numbers, means, medians, etc., right? It's the most basic way of reporting data and therefore more palatable to the general population. So if you are to present the same data in an inferential manner, then it will hamper, the way the general public may be able to understand the data you're presenting to them. So that's why most of these demographic and health surveys will be just presented in a very plain manner through descriptive statistics. Another basic concept that we probably need to understand before we look at the specifics of descriptive statistic is what then is the difference between variable and data? I know from the beginning of this series we've mentioned a lot of in many times the words data and variable. What is the difference between the two? Because when you will be doing the analysis, then we need to define what variable is and what data is and what types of data we'll be handling. So variable essentially just refers to characteristic of a person or object that is being studied, right? Let's use the initial example that we mentioned where we are looking at maybe the prevalence of diarrheal diseases or incidence of diarrheal diseases in informal settlements, for example, in Nairobi, right? Say you have 1,000 study participants that you are looking at. Variable, for example, here would be something like age. So age would be a key characteristic of the study participant, because you understand that these diarrheal diseases may be more common in certain age groups, right? Sex, for example, would be another example of a variable. So they just give us labels or characteristics of what exactly we are studying, the individual or the objects being studied. But in the current case, we are referring to characteristics of study participants. So age, sex, occupation, residence, amongst others, all those would be considered as variable. Now, these variables may assume various states. For example, if you're talking about age, then they'll be expressed in the form of a number, right? For example, 20 years, 4 months, a week, for example, if you're talking about a different age group. So therefore, data here becomes the raw information that we measure, right? Um, Under age, then we will measure age in the form of years or months or even weeks, depending on how you define your age. If it's BMI, which is a variable, then you will measure it in the form of kilograms per meter square. So you will measure it in that form, right? If it's a variable like sex, for example, then you'll be looking at either male or female, for example. So this factual information about the study participants that can be measured or observed is what we refer to as data. So often we will be referring a lot to data, especially when we're looking at types of data and not necessarily variables, because variables just means the container within which within which we contain the actual raw factual information. So if you look at this image here, therefore the variable is just the container, the characteristic. But within this characteristic, what is this actual or factual information that is contained there? So if this variable, the container here, is age, then the data will be the number within this variable, for example. Another important basic concept that probably I'll just reiterate is, now that you know what data is, then what are the types of data? Because each is handled differently when you're performing descriptive statistics and subsequently the inferential statistical analysis. So this data, this raw factual information that can be measured or observed about the study participant can be largely categorized into two. We have what we refer to as categorical and numerical data. Categorical is often sometimes also referred to as qualitative data, while numerical is often referred to as quantitative data. What distinguishes the two is the ability to be quantified. We can quantify numerical variables. On the other hand, qualitative data, these are more of characteristics, more of qualities rather than items that can be quantified. Good example is gender, for example, sex, so to speak. Male vis-a-vis female. That's a good example of a categorical variable. You may not be able to quantify it, right? On the other hand, something like age would be a numerical variable data. We can be able to quantify it, can say 20 years, can say 40 years, 70 years, so on and so forth. Now, when you look at the categorical variable, there are two types. First is a type of categorical variable where you have a number of them, but they don't have any sort of order, so to speak. Let's look at example of colors. So you can have red, green, yellow, brown, purple, so on and so forth. They're just random items. You cannot be able to arrange them in any orderly or meaningful way, right? On the other hand, if you have data of variables such as pain or severity of pain, where you have mild, moderate, and severe, then there is an order of sorts, right? From the mildest form to the most severe form of pain. So there exists a form of order. However, it will be difficult to quantify the magnitude of the difference between each of the categories. So you cannot really quantify the difference between mild, moderate, and severe, unless, of course, what informed mild, moderate, and severe was a continuous variable, maybe a pain score, right? But if it's just plainly put as a categorical outcome, like mild, moderate, severe, then it will be difficult to quantify the differences between the various categories. So these are the two types of categorical variable, and they'll be handled differently when you'll be doing the analysis. Numerical data, on the other hand, can be described as discrete. Discrete, these are all numbers, cannot be divided. For example, number of cars can only have 1, 2, 3, 4. You cannot have 2.5 cars, for example. On the other hand, um, continuous data, they can assume any value along the number line, right? You can have 1.4 hours, right? You can have 38.9 degrees, for example, right? So they can assume any value along the number line. Now, though they can assume any value along the number line, there are two types of this continuous variable. We have what we call interval and you have what we call ratio. So what distinguishes the two? What distinguishes the two is the concept of a meaningful zero. In one of them, zero denotes absence of that value, and that is in ratio. In interval, zero really does not mean that data is absent. Let's use the example of temperature, right? You can have 0 degrees Celsius. It's a meaningful value, right? Zero exists and it denotes a certain temperature. But when you say 0 hours or 0 cars, then it means that that data, that thing you're studying does not really exist, right? So meaningful zero is in ratio. In interval, zero means something. Let's look at this another simpler way of putting it in terms of data complexity. So you can start with the most basic, which is nominal categories, no order or direction of any kind. Ordinal means there are categories that can be ranked. For example, we said pain severity, right? Then under continuous data, where the differences between the measurements exist, right? They can assume a value along the number line, but there is no true zero, right? For example, temperature scale. And then you have ratio. Ratio means they can assume any value along the number line, and zero actually means that that value does not exist. So each of these data again will be handled differently when you'll be doing both descriptive and inferential analysis. Then, having understood why descriptive statistics is important, having understood the difference between variable and data, and having understood the various types of data and variables, then let's look at what are the key descriptive statistics that perhaps are most commonly used and you should be aware of. As you can see, the various types of descriptive statistics, they're categorized based on variables, and that's why I decided to begin by introducing this concept, or rather just emphasizing on those concepts. The most basic of the descriptive statistics that you can do is for the categorical variable, frequency analysis. And here, what you're just trying to come up with are numbers and proportions, right? We go back to our example of diarrheal diseases in informal settlements, right? Um, Assuming you had that 1,000 individuals that you're studying, you can choose to look at something like the sex or gender of the study participants, right? And you can choose to analyze the data and find out what is the sex distribution of the study participants. Then you'll come up with a value like maybe 60% of the study participants were male. That's an example of a frequency analysis for categorical variables. You can express it as a frequency. So you can say maybe 600 of the 1,000 were males. So that'd be frequency. You can express it as a percentage or proportion of the entire study population. So you can say 60 out of 1,000 times 100, then you can say 60% of the study participants were male, for example. And that is one of the most basic descriptive statistics that I think some of you have already done, and you're more likely to continue doing. This is ways in which you can present that data, and that one we can mention it towards the end. Now, for continuous variable, then we usually have these various types of analysis. The first one is what we refer to as the measures of central tendency. Here, we are just trying to answer the question, what is the typical study participant look like, right? When you're looking at averages, for example, what is the mean age, right? What is the median age? What is the mode or the most frequently occurring characteristic of that study population? So there we're just trying to answer the question, the typical study participant, what are the characteristics of this typical study participant, right? When you're looking at measures of dispersion, we're just asking ourselves, if you are to consider the typical characteristics of the study participants, how then do the rest deviate away from that typical characteristic of a study participant? And I think we'll use examples in the subsequent slides to be able to discuss that further. And then distribution of forensics, this one relates to normality of data. Then we're asking ourselves, the characteristics of these study participants, do they assume a normal distribution, or are they skewed towards one direction? And we shall look at examples of that. Let's look at categorical variables. So more often than not, you'll be doing frequency analysis. Looking at this table, this is a table looking at marital status, for example. Just picked it from a study where they're looking at marital status, single, married, and others. So here, you can present this data in this manner, and the interpretation here would be of the 80 study participants, 44 were single. So you can present this data as frequency, where you can just say the actual number, the absolute number that had that characteristics of 44. But you can also choose to present it, and often this is what is recommended, as a proportion of the entire study population. Say this will be 44 divided by 80 times 100, then you'll come up with a figure of 55%. So therefore, categorical variables, their data or results can be presented as frequencies or as proportions. And this is perhaps one of the most commonly performed descriptive statistics. Very simple, very easy to understand, very palatable, and perhaps this is why most of the general or other population and health surveys would, their results would be presented to the general public in this manner. Now, slightly more complex descriptive statistics are the measures of central tendency. So here we are looking at the typical value, right? Um, if for example, if you had 1,000 study participant and you're looking at something like age, you come across 50 patients who had diarrheal diseases. Then you're asking yourself, of these 50, what is the mean age, right? What is essentially what you're asking yourself is, what is the typical age around which you'll more likely to find these diarrheal diseases, for example. So when you're doing measures of central tendency, you're just answering the question, what is the center point? What is the typical value of each of the characteristics of that study population? The most commonly performed measure of central tendency is the mean. Mean just means arithmetic average. So if you are to add the data for a variable, a continuous variable, and you divide by the total number of study participants, for example, then you'll arrive at a mean. So let's take the example of age. So if those are 1,000 study participants, you can sum up their age. When you divide by 1,000, you'll end up with an arithmetic average that we refer to as mean, right? So it's best used for continuous data, which we've agreed. These are data that can assume any number along the number line, any value along the number line, including decimals, for example, right? But more importantly is that it's more useful when you have a normal distribution. And we shall look at what normal distribution is in a few, but looking at this chart, this is a characteristic of a population. Let's say this is age. So here you'll have age of the population. So the typical normal distribution is usually described as a bell curve, where you have a nice bell curve where you have almost an equal number of participants on either side of this midline. That's what is referred to as a bell curve. But when you have majority of the study participant lying on one side of the bell curve, then that becomes a distribution that is not normal. And in such cases, then expressing the measure of central tendency in the form of mean is not usually advised. Why? Means are sensitive to outliers. So outliers are values that are way and over beyond the range of what you'd expect for that characteristic that you're measuring. So for example, if you're looking at age, you might have a study population whose age ranges from 20 to 40, for example. If you're looking at the issue of the diarrheal diseases, then you'd be looking at children under fives, for example. But if one of the study participants who developed a diarrheal disease was 30 years, for example, then that becomes an outlier. So when you'll be doing the arithmetic average, that outlier is more likely to push the mean way and beyond what you'd expect, right? That's why we are saying means are sensitive to outliers, and therefore they're best used when those outliers are not there, when the data is continuous and normally distributed. What happens then if the data is not normally distributed and when you have outliers? It is then recommended that you report your data in the form of medians. Median just means that the middle value, if you are to arrange the data in order. The good thing about this is that since we are not summing up the actual values, we are just organizing them in order, then it's not influenced by extreme values or outliers. So therefore, this is what is recommended when you have such kind of a distribution. So when you have data that is not normally distributed, then it is recommended that you present your data, for example, continuous data, in the form of medians rather than mean. So if it's age, then you can say the median age of that population was X years rather than mean, right? Mod is often used in categorical data to describe or the most frequently occurring value, right? So when you say majority of the population were male, right? So you're saying which is the most frequently occurring categorical variable with regards to sex of that population. So generally mean and median, we use them largely for continuous data. Mod can be used for continuous data, but often we use it for categorical data. We have also agreed that means are useful when you have normally distributed data, and median when you have data that is skewed. General rule of thumb is that the smaller the sample size, the less likely the data will be continuous, right? So if you are dealing with few study participants, then you're more likely to end up using medians rather than means because that data is more likely to be skewed. So these measures of central tendency are often paired with the measures of dispersion. Having understood the typical value, in this case the mean age, then the rest of the study participants, how far away are they from the mean, right? So therefore we typically pair the measures of central tendency with measures of dispersion. Mean would therefore be paired with standard deviation. Median would therefore usually be paired with interquartile range, sometimes also with range. So these are what we refer to as measures of dispersion. They essentially just give you an idea how far away are the rest of the study participant in terms of the various characteristics from the typical value, right? The simplest being range. Range just means the difference between the highest and the lowest value, right? If you had 1,000 study participants, the youngest having an age of 16 years and the oldest having the range of 8 years, I mean the age of 8 years, then you can say the age range for that population was 16 to 80, right? And that becomes range, right? The thing about range, similar to means, is that they are sensitive to outliers because you're just stating the lowest and the highest. So if you have outliers on either end of the spectrum, then you'll have a range that is skewed. Therefore, in situations where the data is not normally distributed, then it's recommended that you use interquartile range rather than range. Interquartile range just looks at the spread of the middle 50%, that is from the 25th percentile to the 75th percentile. So it's less affected by extreme values. Therefore, interquartile range is often paired with median. So it will be reported together. So you can say the median age was 25 years with an interquartile range of maybe 17 to 23 years, for example. Both of them are less affected by extreme values and they are therefore recommended to be used when the data is not normally distributed. Means often would be paired with standard deviation. Here we are looking at how far is the data away from the mean, okay? How far away is this data away from the mean? If you look at the image on the right, this is a theoretical a normal distribution where it's typically described as a bell curve with the mean, median, and mode, all of them coinciding at the midline. This is what is called a perfect normal distribution. So in the normal distribution, usually it is expected that approximately 68% of all study participants will be within one standard deviation away from the mean. 95% would be two standard deviations away from the mean, right? There's a formula of calculating standard deviation, which we can look it up. The good thing about that formula is that it is done in a way that removes the impact of outliers. Because of the way it's calculated, then it's less sensitive to to outliers, and therefore you're more likely to come across standard deviation being used to describe measure of dispersion, even more than mean. More often than not, you'll hear people asking what was the standard deviation, right? More than the mean. So then what is this story about normality of data, having understood the various descriptive statistics? If we look at the image on the right, the small ones here, we've agreed that normal distribution is usually described as a bell curve, right? With the midline signifying the concurrence of the mean, median, and mode around there. So it means 50% of the study participants will be to the left of the mean and 50% to the right of the mean, right? But you can have situations where majority of the study participants may be to the right of the curve, for example, or to the left of the curve. This is what we can refer to as skewed distribution. For example, if you use the example of age, right? If majority of the study participants will be young, then you'll find such a curve. Most of them would be to this side of the bell curve because they're young. If you'll be studying a generally elderly population, of course, with some young individuals, then you expect to find such kind of a distribution, right? These are what are referred to as not normally distributed data, but the typical bell curve is what is referred to as normally distributed data. So in theory, normal distribution is described as a situation where majority of the values cluster around the midline, around the mean, and the tapering on either side of the mean is symmetrical, right? So you end up with this blue curve that you're seeing here. But why then should we be concerned about normality of data? What is the whole point of understanding whether the age of that study population was normally distributed or not? One, it will determine the reporting of descriptive statistics. We've just agreed that when you have data that is not normally distributed, then the appropriate measure of central tendency would be mean if it's normally distributed, or median if that data is not normally distributed, rather than the other way around. The other reason why you need to understand this is that it then trickles down to when you're doing inferential statistics. So data that is normally distributed is subjected to completely different inferential statistics compared to data that is not normally distributed. So if you don't get this concept of normality of data initially when you're doing your descriptive statistics, then it will affect how you're going to do the inferential statistics, and you may end up with erroneous results, right? Because you used statistical tests that were not appropriate for that normality of data. So therefore, it's always encouraged that part of the descriptive statistics should be to check for normality of data, and I shall demonstrate to you how then we do analysis for normality of data. How do you do analysis for assessment for normality of data? We shall look at it using a practical example, but the first one is the most commonly used. So you can generate histograms. These are what we refer to as histograms. And just by looking at the histogram and superimposing line, then you can be able to tell whether the data looks normally distributed or abnormally distributed. For example, the second image, clearly you can see that the data is skewed to this side, and this may not be data that is normally distributed. Another way of looking at normality using graphs is by generating what is referred to as box plots. This is what is referred to as box plots. Box plots is just another way of visualizing the data where you generate such a graph, usually with interquartile range. So this would be the 25th percentile. This would be the 75th percentile. Then this would be the median here. And then the ends of this will be the range of the data from the smallest to the highest. So usually if the data is normally distributed, then you expect to have this middle line halfway between these two interquartile range around there, and you also expect the outliers there to be symmetrically distributed. So if you end up with such a bar or the other one here, then that data may not be normally distributed. The limitation with this is that it may be a bit subjective. This one to someone may not look perfectly normally distributed. So it's therefore recommended that on top of just looking at graphs, then you do statistical tests, and there are two of them, Shapiro-Wilk, and one is a very difficult name. I'll show you how to perform them. They're very simple to do. The only difference is that one is recommended when you're dealing with a small sample size, that's Shapiro-Wilk. But if you're generally dealing with larger sample size, then this second one is called the Kolmogorov test is what is recommended, and I shall show you how to perform this. So usually it's recommended that you combine a graph and a statistical test to determine whether the data is normally distributed or not. In the statistical test, what you'll be looking at is this p-value. If it's exceeding 0.05 often, it would tell you that the data you are seeing is not significantly different from normal, and therefore that data is normally distributed. So those were the basic concepts that I thought are important to understand before we do a practical demonstration on how to perform descriptive analysis. So what are the key steps when you're doing descriptive analysis? First and most important is define the objective. What is it that you want to summarize, right? You want to summarize the social demographic characteristic of a certain population. You want to define or to describe or to summarize the clinical characteristics of a study population, right? You want to describe maybe radiological characteristics of that sample. So define what exactly you want to summarize, okay? Number two is in whatever you want to summarize, then identify the variable types and subsequently the types of data that you'll be handling. This is the example of a study population where we are looking at rheumatoid arthritis patients, right? Rheumatoid arthritis patients in a clinic in Kenyatta, for example. Say we want to look at the socio-demographic characteristics of patients presenting to rheumatoid arthritis clinic at KNH, for example. That is what we want to summarize, social demographic characteristics. So what variables will we be looking at here under social demographic, right? Someone would say age, sex, residence, occupation, for example. All those would fall under the broad objective of social demographic characteristics. But the variables specifically there, you have to define them. Under social demographic, the following variables shall be considered. We shall consider age, we shall consider sex, we shall consider occupation, we shall consider residence, we shall consider cigarette smoking or exposure to fossil fuels, so on and so forth. So identify, and not just identify, define that variable. When you say smoking status, what do you mean? Do you mean active smoking? Do you mean passive smoking? Active smoking, do you mean history of active smoking? Or do you mean, so you go ahead and not only identify, but also define those variable types. Once you define the variable, then you'll go ahead and collect the raw factual information about each variable, and that's what we defined to as data. Once you have that data, then you'll proceed to perform what prerequisites before you do the actual analysis. And the role of these prerequisites that you'll be doing is to be able to make the data easier for you to handle during the analysis. So these are the three things you'll be doing. You'll be doing coding, you'll be checking for missing values or missing data, and you'll be checking for outliers. And we shall have a practical example of that. The reason why you need to do that is so that you avoid errors, so that you avoid misleading results, right? So that you make your analysis easier. That's what we refer to as cleaning of data. Number 4, then you check distribution. For each of the data that you have collected, especially for continuous variable, check the distribution, right? Is it normally distributed or not? So say for these patients coming to rheumatoid arthritis clinic, you collected age as data, for example. Then you ask yourself, of course, I'll present the descriptive statistic for age, but am I going to use medians or am I going to use means? Am I going to use standard deviations or interquartile range? That will be determined by the normality of your data. If that data is normally distributed, then you will present them as means and standard deviation. If that data is not normally distributed, then perhaps the best way to present that mean is by doing analysis and calculating the medians with interquartile range. So therefore, checking the distribution of data is very important. Then you go ahead then and generate the specific descriptive summaries. If it's categorical variable, then frequencies. With continuous variables, then you can come up with measures of central tendency, measures of dispersion, so on and so forth. Once you do that, then you choose an appropriate way to visualize that data. Go ahead and interpret and report clearly using both numbers and visuals. That way, you ensure that whatever you're presenting to the audience, maybe your examiner or to just the general scientific committee, is palatable, so that they're able to not only interpret, not only understand the data, but also to be able to critique your data. So having introduced those concepts and steps, let me use some dummy set that I have. So let me share my entire screen. Okay, so let me exit there. So typically, the commonest used software for statistical analysis is SPSS, the Statistical Package for Social Sciences. It's from the IBM Corporation. the most commonly used by far. There are alternatives that you can use. We have some that require knowledge of coding and may therefore not be very suitable for beginners. These are things like Starter, R, amongst others. You also have another one that is a bit simpler to use as well, called GraphPad Prism. But since this is the most commonly used by far, then this is what we are going to use. So this is called SPSS. For those who don't have it, maybe I can share a link on where to download and license one. So maybe I can share that information later. A free way of getting SPSS. So we'll use this dummy data that I have here. This is just a dummy data, but assuming this was the data from social demographic characteristics of patients attending rheumatoid arthritis clinic at KNH. So you have sheet one and sheet two. So we'll start with the first one. So often you'll find that data will be captured either in questionnaires or Google Forms or Google Sheets, but eventually they'll be transferred to an Excel sheet, for example. And this is one of the easiest tools that you can use to clean your data, right? By cleaning data, what do we mean? Let's look at the data set that we have here. So here we have the participant identifier number, we have age, sex, level of education, BMI, smoking status, this should be systolic blood pressure, and cholesterol levels. So these are the variables, right? These are labels, right? The general characteristic of the study population. Then under each variable, then we have the raw factual information about that variable. For example, now the age is 56 years, okay? So these are social demographic characteristics of that study population. So say someone collected the data in the form of Google Sheets or Google Form or questionnaires, physical, then came and transferred that data to an Excel sheet in this manner. One of the things you have to do is first to check the data for errors. If you look at this data here, then you realize that at this point, we have examples of missing data. So this area like here that I've highlighted in red, those are areas where you have missing data. And missing data can skew some of your findings. So quickly you can be able to identify missing data and you can be able to take care of missing data there, right? You can see there's a lot of missing data here um, around those areas. So I've just highlighted a few of them, right? Then what do you do with missing data? So you ask yourself, why are they missing in the first place? Is it an issue of transfer from whatever it was collected? Was it that it was left out erroneously? If so, then you look for the raw data sheets and you re-enter the values here, right? If it's that that study participant did not have that data or that data was not collected for that study participant, then ask yourself, will it significantly impact your result? If you had to remove that study participant, say you had proposed a sample size of 58 and you have 60, right? If you had to leave out that study participant who has many missing values, then it will not really affect your original sample size, for example. So that's one of the things that you do during data cleaning. Identify missing data, right? Identify errors, because when you'll be transferring this data to SPSS, then it will affect or it will interfere with your analysis. Let's take example of sex here. So we have sex, which is a binary outcome, so it can either be male or female, right? But here, under serial number 10, you'll see that under serial number 10, the sex has been put as F. Now, if you are to transfer this data in this way to the SPSS, SPSS will read F as a distinct category, right? As a distinct category. So therefore, if you run the descriptive statistics frequency of sex, then it will give you 3. So the first sex will be male and it will give you a percentage, female and it will give you a percentage, and F will be considered as a separate sex. M would also be considered as a separate sex. So during data cleaning, then you identify such errors of categorization and you correct them appropriately. So this one will put, for example, female, and this one will put, for example, as male, so on and so forth. So that's the second role of data cleaning. So the first one we've said you're identifying missing values. The second one, we are just trying to identify consistencies in categorization so that you don't end up with erroneous categorization. The third one is to identify extreme outliers. Extreme outliers. Look at BMI, for example. We know that the normal BMI ranges from 18.5 to 24.9 or 25 thereabout. Of course, above 25, then we have categorizations into obesity and the various, into overweight and the various grades of obesity, for example. It's therefore unlikely that you'll have someone with a BMI of 2. With your knowledge of how to calculate BMI, then it's unlikely that someone will have a BMI of 2. Then you ask yourself, why then do you have such an extreme outlier with regards to the BMI? Because definitely, if you are to incorporate this data in the calculation of your mean BMI, then it's going to affect the mean. It's going to affect the result that you're going to get. If you're to do range, then you'll have an absurd range of 2 all the way to, for example, 36.1 here, right? It's unlikely that someone would have a BMI of 2. So during data cleaning, then you also identify such outliers and you ask yourself, then, was this a transcriptional error? Is it that when they were transferring the data to this Excel sheet, then they left out a value? Was it 20, for example, right? Or was it 26 and someone left it out? So it's upon you to then verify this study IDs, this study participant number 2, go back to the data collection sheet and counter check this BMI, right? And put the correct value. If you're not able to get the correct value, then it's recommended that you just leave out these altogether rather than use such an erroneous and extreme value. So that's the third thing during data cleaning. So the first one, I've said identify missing values. Second thing is check for consistency of categorization. Third thing is to identify the outliers. Of course, the fourth thing is just for you to be able to prepare the data in readiness for transfer to the SPSS. Okay. So by doing those three things, then you'll have achieved the fourth objective, where then you'll have a clean data sheet that can then be transferred to the analysis software. So this is a very important step. So don't miss this out, because if you do so, then you'll see you'll be introducing errors to your analysis, and this definitely are going to affect what you will get in terms of your results. And I'll give you examples using missing data, for example, and outliers. So we leave that one out. So assuming you clean it out and you end up with such a clean, this one here, with such a clean data sheet where there is no missing value, all the categorizations are consistent, you can't see any extreme outlier, and the data sheet is generally clean, right? Then you end up with a clean data sheet that you can then transfer to the SPSS. Now, there are many ways of transferring this data to SPSS. One is to copy paste from the Excel sheet to SPSS. There's another way where you can save this data in a format that can be accepted by SPSS. So let me just try and save it here. And you can be able to see formats, like for example, XML sometimes can be accepted by SPSS, and some form of CSV, for example. Now, the issue with transferring the data directly or saving it into a format that can be absorbed easily by SPSS is, unless you're very consistent with your coding, then you can end up with errors, right? So if you are just a beginner in the journey of analysis, then I'd recommend that you just load one category at a time, right? You load one category at a time. So that is what goes on to data cleaning. Apart from cleaning, then there's a concept of coding. Now, you realize that because of the many words that can be found in various variables, for example, male, female, sometimes when you're typing this, you can leave out a word. For example, someone can just type female like this. Someone can type male maybe like this, forgot to put an A, or something like this for female, right? These are errors that can occur during typing. They're typographical errors, right? One way to avoid such typographical errors is by converting these categorical variables into absolute values. So you code them. You code them in a way, for example, consistently, you can say instead of putting male, I can assign male a value of 1, and I can assign female a value of 2, for example. Just 1 minute. Sorry for that. So you can choose to do this. You can assign these various categories values. The good thing of assigning them values then is that it's easy to input these ones with very fewer chances of erroneous or typographical issues. So sometimes you can transform your datasheet into search. But for this, then it means you need to know what 1 stands for. 1, for example, we've agreed was male and 2 was female. You can do the same for education level, 1 to be primary, 2 to be secondary, and 3 to be tertiary, right? This is a very useful thing to do because it avoids a lot of those typos when you're transferring the data to SPSS, right? But then it means you need to be in a position to consistently code them in a manner that you won't forget, so that you don't mix up 2 versus 1 in one category versus the other, right? So often it's recommended that when you're coding, put the key here so that even if you are to forget, you can always refer to the key. So you can say key 1 male, 1 female. For the other one, you can say primary will be 1, and then secondary 2. So you see now, for example, I've already misspelled this one, and this would have gone to SPSS, and then it would have given me issues during the analysis. So you can say secondary 2, then you can say tertiary 3, for example. So it's encouraged that if you decide to go that route, then put up a key that you can always make reference to, right? So assuming you are to go that route of coding, then you'll end up with data that looks like this, where instead of words, you have values that mean certain things. So this is what we refer to as coding. So when we say cleaning, it just means you are identifying errors, missing data, and outliers. So when we say coding, it means you're converting these categories into absolute values for ease of loading to the SPSS. Once you do that, then the next thing would be to load the data to SPSS. So when you open SPSS, let me close this. Many tables, maybe perhaps let me close these ones that I'm not using it now. So we have, good. So I'll just close this and open SPSS again. Once you install SPSS and you open it, this is the first thing that, the first window that will come up. Sorry, my processor is a bit slow. Just bear with me. Or rather, the laptop's processor. So assuming you had some work that was ongoing, then you'll get this auto recovery window. Otherwise, this is what you'll get. Up there, it will be written untitled because this is a data set that is not titled. So down here, you'll see two things, data view and variable view. That's why I started by introducing the concept of data vis-a-vis variable. You have to start there. We say the first step in descriptive analysis is to define your objective. So let me open up a Word document. And let's say our objective is to describe the social demography demographic characteristics of patients pending rheumatoid arthritis clinic, not KNH, for example. You can define a time period or you can just leave it as is. So maybe that is our objective, right? So then what variables will you be looking at? So under social demographic characteristics, then we have variables like age, we have sex, we have occupation, we can have smoking status, we can have residency, etc., and so on and so forth. So you have to define your objective, um, 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 uh, mention your variables, and these variables can be in this form, either continuous variables like age or categorical variables like sex, occupation, smoking status, residency, right? Um, so once you do that, then um, you capture this data when you'll be doing a data collection, and this data will be in this form. So you'll have your age, your sex, education level, BMI, etc. Then you proceed to come and load it to the SPSS. Once you open, then you have your variable view and the data view. So variable view is this page. If you click the data view, it will take you to the other page, right? What you'll notice is that in the variable view, then you will have this wordings on top there. So name, type, width, decimals, labels. I'll explain what each means. But what you're putting here is these variables that we mentioned that you need to define early. Okay, so you put these ones under the variable view. Okay, so let's look at the data we have here. The data we have here as so let me split my screen for ease of visualization. So on the right, I have my Excel sheet. On the left, I have the SPSS with the variable view opened. So the first variable I have here is ID. So here I will put study ID. Now what you'll realize is under name, SPSS does not allow you to put space. Okay, so if I put space, you'll see what SPSS tells me. Variable contains illegal character. So under study name usually does not accept spaces, right? So if you have to put something like, so let me put the rest. So we have age, we have sex, we have education. So this is education level. So if you put space and then you put education level with a space, then it will not accept, right? So here you have to say maybe education level, okay? Then we have BMI. We have smoking status. Sorry, so smoking status. We have blood pressure and you have cholesterol. So these ones you can use abbreviations, but if you want to put the whole title, then you put it under label. So label accepts spaces. So for example, if you say study ID, it will accept. If you say education level, it's going to accept. If we say blood pressure or even systolic blood pressure, it's going to accept, right? So here often you use abbreviations. So you can just, for example, say education level. Okay, but then you go ahead and under label put the full term so that in case you forget what it was, then you can always make reference to it. So if we summarize this one as SBP, which is accepted systolic blood pressure, if someone else were to open this data set and does not know what SBP means, by checking the label side, then they can be able to know what it stands for in full. And did one cholesterol. So this is what you put under variable view. So under variable, put your variables there. And why did we need to understand the various types of variable? This here, type means type of variable. Okay. So for example, age is a continuous variable. It's a numerical variable. So therefore, it will remain as numerical. Sex, on the other hand, is not a numerical variable. It's a categorical variable. So if you leave it as numeric, it will not accept a word. It will only take number. Let me give you an example. So once you put your variables, if you go to the data view, then on top there, you'll now see your variables there, the ones that you typed up. Okay, so the role of the variable view is for you to put all the variables that you're considering. And when you go now then to the data view, under each variable, then you can feed the raw factual information, aka data. For example, age, we've left age as a numeric variable, and it would therefore accept numbers. So if you put 55, 23, 12, or 21, 12 like this, it will accept. On the other hand, we've left sex as numeric. If you decide to put male, it will not accept because you've specified this as a numerical data. The SPSS therefore expects you to put a number here. So then what do? You convert this and specify it as categorical. Now, SPSS does not have the term categorical, but in its place, it has the term string. So you can use the term string. And if you specify it as string, then it can accept a word like male, can accept a word like female. That's why it's very important for you to get the basics right. Understand what a variable is, what a data is, what are the various types of data in variables. Okay, so that we've understood what name means. So this is variable name. You've understood what type is. Essentially, we just mean the type. Is it categorical or is it numerical? Width just means the number of letters that can be accepted for a string value. Okay, so for example, here these are 6 words, perfectly okay. Assuming there were more than that, it cannot. So you see, I'm typing, but it can only take a maximum of 8 words. So if it's a string that has many words, for example, secondary. Let me type secondary. Secondary. I think there's an N some. So you see, it will not take N. So let me use, so it will not take Y because here I've specified the width of that string to only 8 letters. So for me to for it to accept more, then I'll need to edit this and put maybe 22 letters. And if you do that, then it will be able to take any additional letter there. So for string, always counter check the width so that you're able to transfer without losing any words there. So always increase the width of your letters, particularly when you're dealing with string variables. Okay, so this one I'll just reset it to where it was. But since it's male, female, which is maximum of 8, I think that will be okay for sex. But for education, definitely it will not be okay because secondary is 9 words. So I'll need to at least allow a width of 9 and above. Okay, so on and so forth. So that is study name type with decimals. Just means for the numerical variables, what number of decimals will be presented in the data view. For example, you can see here, it automatically puts 2 decimal places. If you reduce it to 1 decimal place and go back to data view, say you had 56.89, okay, under age, and under age you reduce it to one decimal, then you'll see it will summarize it to 56.9, right? So under variable view, you can tweak the number of decimals that you want there to be in your data, right? Under labels, we've agreed that you can specify the full name of the variable there. You can even add spaces, okay? The other thing that you'll see here is values. So what are values? Values are useful when you have coding, okay? So for example, if you look at sheet 2 of the Excel, sex here was coded into 1 for male and 2 for female, okay? 1 for male and 2 for female. So if you are to come here and specify sex, um, you can put maybe 1, 2, 1, 1, 2, for example. Sometimes it can be easy to forget what 1 is and what 2 is. So how then do you ensure that that information is captured? You come to values, and under sex, under value, you will see these three dots there. When you click on it, then you can be able to put a label for each value. So for example, value 1, the label is male. You add. Value 2, the label is female. This is used when you've coded your data. So if your data looks like this, so that again in SPSS, you don't forget what 1 was and what 2 was, then you specify them under values. So once you do so, you put OK, and you can see it will save. It will save 1 as male and 2 as female. So even in your results output, 1 will be specified as male, 2 will be specified as female. Okay. So I'll leave it at that. In terms of the variable view, these are the ones you need to understand, the simplest ones. So variable name, variable type, variable width for string or categorical, decimals for numerical, label, full name of the variable name, values, you use them if your data is coded. Okay. So these are the basics that you'll need to get when you're dealing with the variable view. So I'm going to reset all this. So let me delete all these things that I've coded there. So these ones I can just reset them to where they were. This one is misbehaving. Okay, fine. Can just leave it at that. So let's use this data that is not coded, which means that age will be numeric, study ID will be numeric, sex will be string or categorical. So this one, let me also specify a string. BMI there is numeric, it's a number. Smoking status is binary, so categorical. So here I'll put it as string. Blood pressure and cholesterol, they're all numerical variables, so I'll leave it as that. And the education level, the longest word is secondary, so it has 9. So I've allowed for more. I can even put give it more allowance there. So once you do that, so long as the variables here, they are ordered in the same way as in the Excel sheet. For beginners, then I'd advise that you copy one at a time. So you can, SPSS allows copy and paste. So you can copy that and you can paste it under study ID like that, right? If we can do the same for age. But remember, if you don't specify the data type correctly, SPSS will not accept. So it's only accepting because we've specified this one as numerical. We specified sex as categorical, so it will accept because we've put it as string. So we can copy this and we paste it here, and it will accept, right? If these variables are ordered in the exact same manner as in the Excel sheet, what I sometimes just do is that I'll take all of them. So long as the order is correct and tallies with what is in the Excel sheet, and I'll just come here and I'll paste it once and it will accept, right? So that's one way of transferring data from Excel to SPSS. So for beginners, I'd encourage that, since you'll have more control over what is being transferred one at a time, right? So we've transferred our data to SPSS, right? Through copying and pasting. The other way of transferring is by loading the Excel sheet directly here, okay? But that will present certain challenges. Let me first save this, then I'll show you the alternative method. So let me save it in my desktop as dummy results. So always remember to save your results or your data or your SPSS file, because sometimes things happen. So you cannot save it. Oh, not specified. So in desktop, let me save it there. So I've saved it as dummy data. So let me close it. No, so I've closed it. Let me show you an alternative way of transferring this data. So say I have this data saved somewhere in my laptop. So let me save it in my desktop as descriptive analysis dataset. So let me save it as Excel. Let me just save it as an Excel workbook for now. Then let me open my SPSS. So if you had ongoing work with SPSS and you closed, usually it prompts an auto recovery, same as in Word. So you can see 7 minutes ago, we don't need this, so I'll just close. So this is what you get initially. So if you go to File, and then you go to Import Data, right? Import data. So you can see the various formats from which you can import. So you can import it as an Excel sheet, as a CSV sheet, as a text sheet, so on and so forth. So what we have is saved as an Excel. So I'll click Excel and I'll go and locate it. So you see under desktop, we already have that data saved in this manner. So I'll click on it and I'll click open. So it's just going to transfer the data to SPSS. So this is a preview. So it will give you a preview where you have your ID, age, sex, education, BMI. So it has already auto-detected the various variable types, and it has categorized it accordingly. So it knows that sex is categorical, education, so on and so forth. Then it gives you these options. So you can choose to ignore or remove string values, or just do these ones. Often, if what you are seeing here is satisfactory and represents what you have, then you can go ahead and import. So you click OK, and it will import your data. Now, the issue with that is that if you have any other data in your Excel sheet, it will be captured. You see what we were doing there under key, male, female, whatever we were putting there, it's already been captured. Okay, it's already been captured. So these ones you can delete. The other limitation with direct importation is that if you've not specified the variable, then they will present in this manner. They'll just be called V9, V10, V11, V12, right? So therefore, it's important that for you to be able to import easily, make sure in the Excel sheet you've specified the variables up there so that SPSS is able to auto input the variables in SPSS. If you don't, then they'll just be called V1 to V12 depending on how many variables you have. So these ones I'll just go ahead and delete, since they are variables that we don't really need. So that's another way of importing your data. So we had an objective to describe the social demographic characteristics. So we've defined our variables. We went ahead and collected our data in the form of maybe data sheets, raw data sheets, or Google Forms. Then we capture that data, we transferred it to the Excel sheet. It had a lot of issues, so we did data cleaning. So we removed the missing, the ones we repopulated the missing values, the one that we didn't have, we deleted. We checked for consistency of categorization. We removed outliers. We essentially cleaned up our data. After that, some coded, some didn't code, which is optional, but it's encouraged. After doing that, then we imported our data to SPSS, and this is the imported data. Then what do? Remember the fourth step in the analysis of this data. Remember this step. So we said we've defined, we've identified the variables, we've cleaned the data. Then we check for normality, particularly for categorical, for continuous data. Okay. So we have an example of a continuous data there that we call age, BMI, blood pressure, and cholesterol, right? Before you even go ahead and generate means, medians, etc., we need to understand, is this age, is the data under this category of age normally distributed? So that if it's normally distributed, then we will rather calculate means. If this data is not normally distributed, then I'd rather calculate median. So how do we check for normality? So in SPSS, there are tabs up there. We have edit, view, data, transform, analyze, so on and so forth. Okay. So usually you can begin, or rather you can use this thing is impeding my, so under analyze, so you go to analyze, and then descriptive statistics. So you can see there, you have descriptive statistics, and you can see all of them: frequency, descriptives, explore, cross tab. So this is the tab that you use for descriptive statistics. So you come to analyze, then descriptive statistics. Okay. Now, if you want to check for normality of data, you use the third tab, that is explore. So you click on explore, and it will give you this table or this prompt where you have your variables there, and it will ask you to specify these ones. So just use the dependent side. So you can put your age, so you drag it there, BMI, blood pressure, and cholesterol. So if you click on it, click on the arrow, so it will be brought to the dependent list. So remember, we're just checking normality of continuous data. Okay. And plots, you'll see this tab here written normality plot with tests. Where did I find the normality test with plot? Once you load them here, click on plots. You will see this tab here. You check that box. If you check that box, it's going to show, to give you the normality tests. But remember, we agreed there are two ways of checking normality of data. One is using histogram. So tick on the histogram, and then also tick on normality plots with test. So this one will do the Shapiro-Wilk. This one will just give you the histogram. Click on continue. Let it display both the statistics and plot. So you click on plot and you click OK. So you'll get such an output. So it's still analyzing. So give it, so this is the output that you will get. So there's always a summary here. Summary just tells you you've put 4 variables. Each variable had 100 entries. All of them were present. There were no missing values. So usually in every SPSS output, always check the processing summary, because it will tell you if there are missing values. So there are no missing values. So we have all the data. Okay. So it has calculated the descriptives, but for each of the variable, it has calculated both the mean, the median, the standard deviation, interquartile range. So it has gone ahead to calculate all of them. It's a default thing. But then, which of these are we going to use for age, for example? For example, here we have an age of 43 with a standard deviation of 14.9. We have a median age of 42 with an interquartile range of 26. So which would be appropriate to report here, because you have both. The same for BMI, you have both the mean and median. The same for blood pressure. So how do you determine which to report or which way to report? Then go and check the normality of your data. First, we agreed that we have graphical ways. So it has generated for you a histogram. And by looking at this histogram, then you'll understand or appreciate that this data does not really look normally distributed. Majority of data is skewed to this side. And if you are not too sure, you can also double click on the image. If you double click, it will give you a format that you can manipulate to add certain elements. The element that you want to add is a distribution curve. So it will put for you that line. And if you close, then it will put for you a distribution line. And you can see that majority of this data is skewed to this side. This data really does not appear to be normally distributed just by visual inspection of the histogram. Let's see for BMI. How does BMI look like? So this is the histogram for BMI. Just from looking at it, it has some semblance of a bell curve. But to be sure, just superimpose a distribution curve. And if you look at that distribution curve, it has a semblance of a bell curve. The only limitation with looking at these charts is that they can be a bit subjective, but at least it gives you an idea as to whether this data may be normally distributed or not. But by looking at this, looks like it could be normally distributed. So histogram is one graphical way of confirming normality. Is there an alternative graphical way of confirming normality or at least assessing normality? Yes. We also mentioned the box plots. These are an example of a box plot. So we agreed that this edge didn't really look normally distributed from the histogram. How about from the box plot? So box plot looks like this. So it gives us a median, which is that thick black line there. It gives us a 25th percentile, which is the lower line. It gives us a 75th percentile. So this is 50%, the middle 50% of the data. The median is here. The lowest value would be down here. The highest value will be down here. So if that data was normally distributed, then we'd expect this line to be closer to the midline around there. So by also looking at the box plot, doesn't look that this data, especially age, does not look like it's normally distributed. But we've said that the graphs can be a bit subjective. Then is there an objective way? Yes, there is. So remember, when you are doing normality, we ticked a box for normality tests, and it has generated for us both Shapiro-Wilk and this other difficult one called Mogorov. Remember, each of these variable has 100 inputs. We agreed that if you are dealing with a smaller number, generally less than 30 but can be accepted to up to 200 thereabout, then you can use Shapiro-Wilk. This significance SIG is what we look at. It's the p-value for this test. If that p is less than 0.05, it tells you that that data is significantly different from what you would see in a normally distributed population or in a population that has a normal distribution. Therefore, it tells you that that age is skewed. It's not normally distributed. On the other hand, BMI, the p-value is greater than 0.05, the same for blood pressure and cholesterol. Therefore, BMI, blood pressure and cholesterol, they assume a normality, they assume a distribution that is normal. Of course, may not be perfectly normal because perfectly normal distribution is theoretical, but it has a quite huge resemblance to normal distribution. So therefore, age is not normally distributed, but BMI, blood pressure, and cholesterol appears to be normally distributed. And there's a concurrence here between Shapiro and Kolmogorov test here. So therefore, if I were to run descriptive statistic, I'd therefore rather report age as medians an interquartile range because it will be less affected by outliers. I mean, these are not normally distributed data. And for BMI, blood pressure, and cholesterol, I'd rather report it as medians, as a mean and standard deviation because this data is normally distributed. That's why it's very important for you to do this test for normality. It will guide you in reporting of the descriptive statistics and subsequently when you'll be doing inferential statistics. So having understood that age is not normally distributed but the rest are, then we'll go to our descriptives. So for age, I'll pick a median of 42 and an interquartile range. This is the interquartile range of 26. It's essentially from 25th percentile to the 75th percentile. So I'd say in my results, I'd say that the median, so I'd say 100 participants were included in the study, right? I'd then say the median age, not mean, because the data is not normally distributed. So the median age was, and then you can counter check here. What did we get? So we got a median age of 42 with an interquartile range of 26. So I'll say the median age was 42 years. In bracket, I'll put the interquartile range IQR of 26, right? It's a measure of dispersion, just tells me the rest of the variables, how far are they from the median age. So the median age was 42, right? But if I'm to report the BMI, for example, since the data is normally distributed, the appropriate way to report it would be using mean with standard deviation. So I'd therefore say, so the median age was 42, but the mean BMI was, so I'd look for the mean BMI. So it was 24.8 with a standard deviation of 4.1. So I'd say it was 24.8. Standard deviation usually is reported using a plus or minus. So I'd put plus or minus. I think it was 4.1 kilogram per meter squared. And this one, and use it as a superscript. I'll just leave it at that, for example. So you can see the rationale of me using median here and mean in BMI is primarily driven by my understanding that this data had different distribution types, right? And the best way to present them or to present them would be in that manner. Okay. So if you are to run your descriptive statistics, then so let me close that first and go back to our data. So you can use the tab of Analyze, Descriptive Statistics, and then Explore. That's one way. Then you load your continuous variable. Remember, this one is done for continuous variable. And then under statistics, of course, they've auto-ticked descriptives. And under plots, make sure to check normality and histogram. So this one is useful for continuous data, and it will give you all the descriptives for continuous data, including, so you can see all the descriptives for each, including data on normality, and that will help you describe the data. Now, assuming I wanted to look at the frequency of various sexes, for example, so I'd come under frequencies, okay? So I've still used the tab of Analyze, then Frequency. Then here, you see the statistics that we can get here are still for continuous variable, okay? Because we are looking at frequencies, so you can talk about quartiles, mean, median, mode, standard deviation, variance, range, amongst other things. So you can choose to also use this when you are doing your continuous variables, okay? Or you can use the explore options. The reason why I'd suggest you use the explore is because it also gives you the data for normality in the same tab. Nonetheless, this one will still give you all your descriptives that we are talking about. It will still give you your mean, your median, standard deviation, range, and even the percentiles, right? So when you're doing continuous analysis for continuous data, so you can use the frequencies here, or you can use the explore tab, okay? Assuming you wanted to do proportions for various categorical variables, then I'd use descriptives here, and then I'd choose my variables. Just a minute, so let me go to descriptives. And then, so let me remove these ones first, all of them. So let me take sex, for example, as an example. So you can see under frequencies, it will give me a breakdown of sex, right? It will give you both the frequency, which you've agreed is one of the measures for categorical data. So 40 of the 100 participants were female. But it also gives you a percentage, which is also the proportion. 40% of the study participants were females, okay? So you come to analyze descriptives, frequencies, and you can load all of them at the same time. And you can decide to kill two birds with one stone, not only get the actual values, but you can also generate charts. So you can decide to put bar charts, for example, for each, or pie charts, so with percentages in the charts. So if you click OK, it will give you both the frequency table, so for sex, male, female, for education level, primary, secondary, tertiary, for smoking status, whether yes or no, and it will give you both the frequency and the percent. And down here, it auto generates for you the pie chart, right? So for example, for sex, you have male and female. For education level, primary, secondary, tertiary. For smoker, yes, no, right? Now, in the frequency table, one observation that you should be keen on is this concept of percent and valid percent. What's the difference between percent and valid percent? Valid percent gives you the percentage after removing missing data. Let's use an example. Say study participant number one, we didn't have data for sex, for example, it was blank, and went ahead and did descriptive statistic for sex. So let's just use sex alone. So it will give you this. So you'll see male, female, but there's one blank there. This is missing data. So it will tell you that of the 130 participants, 40 were males, 40 were females, 59 were males. There is one that didn't have any value. It was not a valid value there. So if you are to do the percent, okay, then it means that the proportion of females will be 40 over 99 and not 40 over 100. So therefore, the percentage there would be 41% rather than 40%. And the same for females. So the reason why you need to be checking the percent and valid percent is sometimes you may have missing data. So if you compare that table with this one here, look at this frequency table. So all of them were valid, 40%, okay? There is no other additional blank value there, okay? So all of them were valid, but if you look at this other table, we have a blank space there. So if you have to calculate the proportion, then it will not be 40%. It will be 40 of 99, not 40 over 100, which would be 41%, okay? So let me go back and replace what was missing. So I think this was male. And if you reanalyze, then that issue should be gone. So once you do that, then you see we don't have any missing value. So for descriptive statistics, you can calculate the measures of frequency, for categorical variables, both frequency and percent. For continuous data, I've shown you how to calculate the test for normality, where you come to the tab of Analyze, Descriptive, and Explore. Then under Statistics, you can check Descriptives. Under Plots, check both histogram and normality, and click OK. And it will give you your results. So it's still generating. Good. So there we have the case summary. You have your descriptives, and you have your tests for normality there, together with the plots, histograms, and your box plots, right? So in a summary, these are the basic descriptive statistics that you'll be doing. But is there a way of tweaking, a more slightly more complex way of doing the descriptive statistic? Yes, there is. I'll show you two things quickly because our time is running out. Say you wanted to check how education level varies with sex, for example. You wanted to see is there a way in which this education level varies with sex, right? For that, you use a function under descriptive statistics that we call cross tabulation. So you click cross tabs. So you go to Analyze, Descriptive Statistics, and cross tabs. So cross tabulation allows you to essentially cross-analyze two categorical variables. So you can put sex and education level, for example, right? So you can display bar charts for it. These are the statistics that we will do next week when we'll talk about hypothesis testing. Then I'll talk to you about what chi-square is, what McNemar test is, and Cochrane and all those other things. But for now, just ignore that. So just put the two categorical variables. Remember, it will not work for continuous variable, just for categorical variable. Now, if you click OK, it will give you such an output. It will stratify for you the various educational levels of education based on sex, or the other way around. So here you'll see that it will tell you among female, this is the distribution of the education level. Among males, this is the distribution of the education level. And you can do it the other way around. You can decide to reverse that analysis. So you can say, so let education level be there and sex be down here, and it will still give you a similar output, where now you're looking at sex distribution across the various educational levels, and you can be able to quickly say, if you are to look at secondary education, there are significantly more, rather it looks like there are more males than females there who have achieved secondary level. But if you are to look at tertiary level, looks like, I mean, not much of a difference in the sex distribution among study participants who've achieved tertiary level education. This is what we refer to as cross tabulation, and usually the output is what is referred to as a clustered bar charts. Clustered bar charts in that you're able to visualize two categorical variables in one bar chart. Okay, that's one way of tweaking your descriptive analysis to get a slightly more complex output. The last trick I'm going to show you when it comes to descriptive statistics is transforming variables. So sometimes you want to visualize data in the form of categories for continuous data. The commonest would be age. Say you're interested in age groups, not just the raw age of study participants, and you want to convert this into age groups. You want to say, for example, how many participants were between 0 and 10, 11 and 20, so on and so forth. Then you use the option of transforming. So you can transform by recording into a different variable. So you go to transform, record into different variable. So you choose what you want to record. I want to record age. And I want to, so the output variable would be a categorical one. So I'll just call it age cat, or categorical uh, age, for example. So this is what I want to I want to transform age to a categorical variable. Age was a numerical one. I want to transform it into a categorical variable. So then I'll go ahead and specify the old and new values. So I'll click on it and then I'll come here and specify. So what do I want to specify? So you can use range or these other ones. So I want to say if the years are between 0 and 10, okay, I'd classify it as category 1. Okay, then I add. If the age is from 11 through to 20, they'll fall under category 2. If it's 30, if it's 21 to 30, I'll categorize it as number 3. If it's 31 to, let me just skip because of time, to 50, I'll categorize it as 4. And then if it's 51 through to the highest, I can just say 51 through to the highest value, I'll categorize it as 5. So essentially, I'm transforming what was initially continuous into these 5 categories. Then I'll click continue. Then okay. So once you do that, then a new variable will be added there. Now, what is different about this? We've transformed this continuous into these categories, but we will need to specify those categories because they are categorical, they are not numerical. They are categorical in the sense that we said 1 is age group of 0 to 10. 2 is from 11 to 20. 3 was from 21 to 30. 4 was 31 to 50. So this is 4. Sorry, 31 to 50 was 4. Divide that. Oh, sorry, 4. 31 to 50. And then 5 is anything above 50, like that. Okay. So what have I done? I've transformed what was initially a continuous variable into categorical variable, into 5 categories. So if I want to check that those distributions, I'll just come here to frequencies and I'll just load that age categorical, and then it will give me the distribution of those ages. So therefore, I can therefore know how many participants were aged between 31 and 50. So there were 43 participants out of the 100, so 43%. So that is another useful function when you are performing descriptive statistics over and beyond the usual mean, median, frequency. Then you can do cross tabulation and transformation of variables, and that's an example of how to do that. Okay, and therefore once you get your outputs, then you'll report them in prose form as we've done, often attached or accompanied by various ways of visualizing the data, and those are very straightforward ones. If it's categorical, you can report them as pie charts, useful when you have fewer categories, maybe 2 or 3. If you have many categories, you can decide to use bar charts, for example. For continuous data, you can use histograms. They are useful, especially for continuous data, because it not only gives you a way of visualizing the data, but it also affords you the opportunity to inspect the data as to whether it's normally distributed or not. Same for box plots, okay? Same for box plots. Scatter plots is the equivalent of cross tabulation, but for continuous data. So you can see how does BMI vary with age, okay? Usually you'll get a line of base fit that shows you if age changes, how does BMI change, for example. But scatter plot, I'll leave it at this point for now because we will talk about it more when you'll be looking at inferential statistics. As another simple way of visualizing data is just by using tables, frequency tables. For example, these are characteristics of study participants attending rheumatoid arthritis clinic in Kenyatta. So I did the descriptive analysis, frequencies. Let's look at the example of anti-CCP. We found that 113 of the 193 study participants had a positive anti-CCP antibodies at diagnosis. So I'll report it as the such, and I can present this data in the form of a table in that manner. So I think in a nutshell, that's all I had for you. There are a lot more things we can discuss under descriptive analysis, but I think that pretty much covers the basics. We will look at the subsequent more complex inferential analysis in the subsequent session. I welcome any questions.